what we are going to look at today are a number of, I would say, advanced examples with DP algorithm design. So let's start. The first problem we're going to look at belongs to the genetics line of research. If you remember from your biology days, genes come in 4 variations, A, G, C, and T, and they make what's called a strand, and this is basically your DNA, what define your characteristics. And there are so many of them that working with these 4 symbols and trying to identify the different human characteristics, the readiness to a specific disease or a specific health condition for a specific human being requires the analysis of these genes and figuring out certain patterns in them. So, having refreshed your memory with a bit of biology, let's actually start to look at what can we do with these sequences. Now, the most basic thing you can do is what's called the sequencing itself, which is building up the sequencing. Okay. Now, obviously, this is not a computer science problem. This is it belongs to the realm of other research areas, and it is the main activity done within the genetics community. This notion of sequencing. Okay. It turns out to be quite important because if you identify a specific sequence of DNA to be associated with a disease or a readiness to get a specific disease or any human characteristic, then you've unlocked one of the keys to understanding the human body. Now, what we actually work with in computer science is the output of the process of DNA sequencing. Okay. Now, ultimately, researchers will, from time to time, will be able to identify specific sequences of interest. However, the size of the DNA is ridiculously large. You know, we are talking about millions and millions of these strands, and consequently, identifying a sequence doesn't necessarily help a lot without understanding the location of the sequence or other properties that are related to sequencing. For example, the proper order of a sequence, or when will the sequence break, and so on. So I'm not going to cover lots of problems here. There's like an endless number of problems, if I may say that, related to DNA sequencing. I will just show you one example of a problem that could be solved optimally by dynamic programming. The problem I'm going to show you is what's called DNA matching. Okay. So after doing the sequencing, we would like to match some of these DNA strands. So it is the process of matching 2 or more DNA strands to find common or different expressions. Okay. Now, DNA matching as well is not a small area. It's a relatively large area. There's lots of problems, but I will look at a very specific problem within the DNA matching problem set, which is called the longest common subsequence problem. Now, given 2 DNA strands or more, let's just focus on 2 because 2 will be more than enough for us to present how can we solve it with DP. If we have 2 DNA strands, we would like to know the longest sequence that repeats between the 2 strands. For example, it could be like the size is 4 or the size is 5. Let's say I give you 2 DNA strands, each one has 500 symbols. So there are a huge number of possibilities here. It could be like there's only 2 strands that represent a sequence that is common between the 2 symbols that are common between the 2 strands. And it could be 500, it could be 300, it could be 200. Okay. So this is what we're actually going to look at. Now, just to define the problem more accurately, what do we mean by longest common subsequence, or LCS as it's commonly abbreviated in the literature? Okay, we are looking for a sequence of these letters that we talked about, the A, C, G, and T, that are repeating, but not necessarily adjacent, in 2 given strings. You see, now it turns out to be 100% computer science problem. S1 is going to be a string, a piece of data structure that's basically you're storing it as a string, okay? It will have these 4 symbols. And S2 will be another string. And now you're required to process those 2 strings to find out the longest common sequence between them. So let me show you here on this example, what do I mean by longest common one and not necessarily adjacent. So let us just do it, okay? Let's try to eyeball it. If you go through the top string, matching it with the bottom string, you should realize that the first common subsequence is GTC. It appears after the first 4 letters in S1, and it appears as the first letter in S2. And then you continue on tracking, you will find that GT also is common. Now, the thing is, we can go backward and forward. We'll move from left to right, finding the common sequence, but we don't have to move the same number of characters in every string. So I am basically eyeballing and trying to see what is repeated between the 2 strings. So after the GT comes the C, and then comes the GGA. It appears in one location in S1 and a different location before it in S2, and then comes the AGC, okay, the A separate, and then GC, okay, and this continues on. Now we are identifying the common sequence between the 2. And consequently, after I'm done with the whole exercise, I will find that the length of the longest common subsequence is 19 characters, and these are this is the sequence that is common. Now, how important this problem is turns out to be tremendously important in the genetics world. Okay, one of the major characteristics of trying to isolate genes that are responsible for certain behavior or certain characteristic or certain disease is to get someone who is sick with that specific, say, disease, and someone who's not, and trying to figure out what is the longest common subsequence, and then comparing that patient to another patient who has the same disease and finding the longest common subsequence. And what they often find is, people who have the same disease will have the same longest common subsequence in a specific location in their DNA, of course, not anywhere. Okay, so it is used in such way, and there's other ways that this could be actually used as well. Okay, now so it is an important problem. Okay, and I hope now you understand what does it entail. Eyeballing it basically will take us back and forth between the 2 strings, trying to find some letter or letters that are appearing in both. And then once we proceed and move forward, we can now go back. Okay, but the thing is, again, they don't have to be adjacent, and this makes it a little bit harder, as you probably noticed, that we're going to go back and forth, advancing in the 2 strings, but not necessarily with the same speed. So let's think first of the brute force solution before we start thinking about the DP solution. So what is the brute force solution? Well, that should be straightforward. What you're going to do is you are going to generate all possible subsequences of S1 and check whether it exists in S2. Okay? Now the problem is, thinking about it this way, there are so many subsequences of S1. It's basically 2 to the m. Okay? That's like a ridiculous number. Okay? So if we're talking about a string S1 that has 32 letters, that's 2 to the 32 subsequences. Okay? So there will be the subsequence of 32 letters, and the subsequence of 31 letters, and the subsequence of 30 and 29 and 28 all the way till 1. And then there are the combinations 1 and 2, 1 and 3, 1 and 4, 1 and 5, and then you go 2 and 3, 2 and 4, 2 and 5, and you keep building all these subsequences, and for every one of them you go and check in S2. Okay? Now each one of the subsequences, when you check it in S2, it's going to be O of n, because you're going to check all of S2 from beginning to end, because it could exist anywhere. Okay? And it doesn't have to be adjacent. So if you're looking for, say, CGT, it could be in S2C, and then some letter, then G, and then a bunch of letters, and then T. but you still have to find CGT, okay? So that's horrible. In terms of performance, we're talking about something that is quite unacceptable. It's 2 multiplied by 2 to the m, okay? Now, if you actually take into consideration that the total length of the human genome, as I mentioned down there, is about 3 billion base pairs, and the length of the DNA in a magnified cell nucleus is about 3 kilometers. Try to substitute that in the formula we have here, and it turns out to be some ridiculously huge number. So obviously, DP will come to the rescue, because this is obviously not a performance that we can achieve anything with. So thinking DP again, we said there are 2 properties we have to think of while we are formulating a DP solution. The first one is the optimality. Can I generate an optimal solution from previously found optimal solutions? And this related to the structure of the problem. Okay, so I need to be able to find an optimal solution to a subset of the problem. And the second problem, or the second property of DP, that we have to have some kind of overlapping subproblems, which means subproblems that keep showing up. So we'll make use of their solution later on. Okay? Now, what we're going to do, I'm going to just jump directly to the solution here. We're going to construct a 2D array. The 2D array will have 2 dimensions. 1 dimension for the M sequence and another dimension for the N sequence. Why am I doing it this way? Because this is my input. This is what I'm trying to work with or process. So I will turn my input into the dimensions in the array, okay? Which is not uncommon in solving problems in DP, okay? Now, what will exist in every dimensions are the letters given in the string. So if S1 has M letters, I will put all of them on the y-axis. Sorry. And if S2 has N letters, I will put all the N letters on the x-axis. Okay? Now, I hope you're already going, speeding up with your thinking regarding what's going to happen. What you're seeing here, this table is going to give you the length of the longest common subsequence. It's not going to give you the longest common subsequence. We have seen this before, that usually the table we solve in is not going to give us the detailed answer or the exact answer. It's going to give us the number we're after, which is how fast or how efficient or how long in this case. Okay, so the last entry is going to be giving us the length of the longest common subsequence between the 2 strings. And as we have discussed before, after filling in the default values, which are not basically where we don't have, we cannot generate a solution, or basically the optimal solution is 0, we're just going to put zeros. Okay. So if I ask here, what is the optimal solution if the N sequence has 0 letters, and for any value or for any number of letters and there are any number of letters in M, the answer is going to be 0, because I'm looking for the length of the common subsequence between 2 strings. So if one of them is 0, if one of them has 0 strings, then the length of the common subsequence is also 0. And the same apply in a reversed way. If the M sequence has 0 letters, and the N sequence, regardless whether it has 1 letter or 2 letters or N letters, if the M sequence has 0 letters, the length of the common subsequence will always be 0, because there is nothing between them that is common, because one of them is 0. Okay, this is what the zeros here are referring to. Now here are the steps. Again, we would like to identify the optimal substructure. Okay, I would like to figure out a way, instead of solving this very complex, very horrendously inefficient brute force solution, I would like to think of it DP. So DP says, oh, I can't solve the initial problem given to me because it's too complex. I'm gonna devise a structure, and in this structure I'm actually gonna use it repeatedly, starting from the most trivial size, and I keep enlarging it, and as I'm doing that, I'm always finding optimal solutions until I find my final optimal solution. So let's think about the structure here. If you're given a string or two strings, each one is of 50 letters. That's difficult, okay? Match 50 letters, 50 letters. That's difficult. If you think DP wise, we would think, oh, why about not doing it with 50? Let's do it with 40 letters. And then let's do it with 30 letters actually instead. And let's do it for 20 letters, and let's do it for 10 letters. Perhaps we should start with 5 letters. Perhaps even we should start with 1 letter. Okay? So the thinking is going to be like this. I will find an optimal solution for 1 letter, and then I will use it to find an optimal solution for 2 letters, where the sequences are of 2 letters, each is of 2 letters. And then if I find the optimal solution for 2 letters, I'm going to use this solution to find the optimal solution for 3 letters. And then 4, 5, or 6, all the way till I go to the 50. Okay? Now I'm making here a simplification which will not really matter that much, but we will have to solve this issue, which is that what if the 2 strings are not of equal length? And that will show up very soon. But if we just think of it just of being of equal length, well, okay, let's devise a scheme to actually match 1 letter and then 2 and then 3, and we keep adding as I already mentioned. Okay? So this is how you should be thinking of it. That the substructure here is basically saying, if you're getting overloaded by the word substructure, it's a substructure. The structure is what you're given initially, 50 and 50. Okay, so I'm going to work on a substructure of it, or a subset of it, if you'd like. Okay, but they historically, the word substructure has always been used, so I just want you to get used to it. Really, it simply means a sub-problem. Okay, but we're going to call it as the literature says, substructure. Okay. Now, and then we're going to devise the recursive formulation, which is coming from our knowledge of the repeating subproblems, the problems that will keep showing up over and over again. Okay, and finally we solve, or basically we fill in the tree. So, how to construct the substructure? I've already described that. Let me read this point. It says problems of smaller size, i.e. given 2 sequences of length 5, let us solve sequences of length 4, and so on. And for to solve length 4, let us solve sequences of length 3. Okay? Now, let's dive directly into what we're going to do. I'm going to read it and then explain it along the way. It says, in every substructure, we come across 2 choices. Okay, so I'm showing you here an example where the 2 strings are not of the same length. Now, when we are actually matching, let's say we stop the clock and then we accept a new element, and then we need to figure out what should we do. So we have 2 options. Okay, the first option is include an element into the common sequence, in this case E. Okay, and solve the resulting subproblem. What does that mean? Okay, now look at X and look at Y. Let's imagine we have been running some algorithm that tries to do the matching. So what I'm going to do is, I'm not going to process the 50 letters at a time. I'm just going to process 1 at a time. So I got the A and I got the Z. They don't match, so I advance. I got the B and I got the B. So I'm happy. I found a common character. So I include my B in my common set of characters, and I will increment my count by 1. The count was initially 0. Now it's 1. Now I move on and I get the D and the E. Okay, they don't match. I move on and there is nothing else left in Y. There is something left in E. Okay, sorry, left in X, which is the E. So I match the E with the E, and I found the match. So I'm happy. Here's another letter that is common between the 2. And I increment my variable by 1. So now I have identified that the length of the common sequence between X and Y, in the first case here, is 2, which is the B and the E. So what this is telling me is that every time I see a new character, I have one of 2 choices. Either it calls me to include it, or I include it in the common sequence and I increment my count by 1, or I don't. Okay? let's look at the example at the bottom, just again to stress the point. I get the A and the Z, so I match, they don't match, I move forward. I get the B and the B, I'm happy, I found a common one, so I increment my counter. Now my counter is 1, and the common sequence is B. I get a D and a D, I'm happy again because that's a common pair. So again, I increment my counter by 1, and now it is 2, and up to now I have found B and D. Next I get a G. Okay, now when I get a G, I'm not going to include it, which I already done when I've seen the A and the Z. Okay, and I am done. So what this means, with every new letter in one of the two inputs, either we include it or we don't include it. Okay, we will include it if it matches with a corresponding letter that we stopped at in the other string, and we don't include it if it doesn't match with the letter we are stopping at in the other string. In the first case, for the E case, you see the D and the E did not match, but when we advanced only to the E, okay, and then we matched the E and the E. So what this is telling me is I should be moving. If you imagine there are virtual pointers that I'm using to move in the string, I should be moving one character at a time in each one of the two strings. I should not be moving the 2 pointers at the same time. When should I move the 2 pointers at the same time? If I find a match, like for example in the case of the B. Okay, but when afterwards I position my pointer in X at D and I position my pointer in Y at E. When I didn't find a match because this is a D and that's an E, I shouldn't move forward past the E in Y and past the D in X. I should do one of them only. I should do one movement only. Okay? Now, with every new letter that shows up, by one movement in one of the two strings at a time, either I get a match or I don't get a match. Okay? Now, this is obviously not the whole solution, but this is very critical to our understanding, because this is what we're going to do. We're going to process these strings from left to right, and we will imagine that every time we're solving our DP table, this is actually the string given to us. We will ignore the rest that's coming later on. Okay, we kind of did the same thing with the knapsack, so we will see the same kind of way of thinking done here as well. But now there's a trick that we have to understand, which is that we can't move both pointers inside both strings at the same time. Okay, I have to move one at a time and then do the comparison, as I've already mentioned. Okay, so let's try to formulate the idea we were just describing in the recursive equation that we're going to use to fill in the 2D array of solutions. Now let me read this. It says, given a sequence X that consists of letters x1 to xm, we define the I prefix of X for I from 0 to m, such that X of I is equal to all the x's from 1 to I. I'm basically trying to say here, I will get the original string, which is X, and I will work with subsets of it, which is going to be X sub I, where every one of those subsets is going to start from the first letter going all the way till the ith letter. Now, I will ultimately reach m, which is the last letter in the sequence, but it will also be of length 0 and length 1 and length 2, or will take the value 0, 1, and 2, and so on. So I will find also optimal solutions for shorter sequences. I'm just trying to formulate it so that I can talk about it as a substructure instead of talking about the whole structure. Now, for any given cell in my 2D array of solutions, that's going to be C of I and J, where I and J are the could think of them as indices into the first string and the second string that we're trying to find an LCS for. Any specific cell in this array is going to be the length of holding the length of the longest common sequence for any given prefix. Okay, so x of I is going to be from 1 to I, and y of j is going to be from 1 to j, where x and y are the two strings I'm trying to match. Okay, basically what this boils down to is that every cell in the array of solutions is going to be a solution by itself, an optimal solution to a shorter version of the array, of the string I'm working with. So when I'm trying to actually find the value of C of I and j, which when I'm trying to find the value for a specific cell in my area of solutions, I will have a number of cases. In the first case, x sub I is equal to y sub j. And I've put here an example for that, where you see the E and the E are matching. Okay. Now, in this case, the Cij or Ci comma j, the optimal solution is going to be whatever I have found before plus 1. Okay, so what that means is I will append x sub I or y sub j to the LCS value. Okay, so if the current number of matching letters was 5, now it becomes 6. Okay, if the current number of matching letters, like in the example in front of us here, was 1, now it will become 2. But to get the current number of matching letters, I have to consider or look at or grab the value from the cell that has the optimal solution without the current letter, which is the E in the X, and also the current letter in the J, which is also the E. So I will basically be grabbing the optimal solution for the string X, where the string content is ABD only, so I was stopping at the letter before the E, so it's just ABD and ZB. So I will append the value that I have found already for ABD and ZB. I will append 1 to it, and this is what the formula is going to be. As you see, if I'm actually finding a matching pair, I will add 1 to, that's the plus 1 that shows up at the end, plus 1 to the optimal solution to the problem without the current letter in X and without the current letter in Y. So it's going to be Ci minus 1 comma J minus 1. This is if they actually match. Now, the second case is when the two letters we're currently considering are not matching. What that means is I'm not going to increment my LCS count. But the question is, what is the optimal solution now? The optimal solution is a solution that I have generated previously. Now, since I am actually introducing letters into my sequence, there are two possible variations for the sequences that I need to consider. In the first variation, I'm going to include the new letter I am currently working with, and in the other variation, I'm not going to include that. So I have put here down at the bottom of the slide the two variations that are already solved, that I have seen before, which is ABD and ZBD without the G. Now, this I have already solved because I am moving into the sequences from left to right. The optimal solution that I should have found earlier is matching B with the B and D with the D, and consequently 2. But I also need to consider another problem of still a smaller size, which is with the existence of the new letter G and omitting the last letter that I have previously entered into my sequence in the second string, or in the second sequence, which is the D that comes after the Z and the B. Because I could actually have a better solution there in terms of the number of the LCS. So I need to consider both, and the maximum of the two is actually my optimal solution, because I'm trying to get as many matches as possible. Consequently, if the letters don't match, I take the maximum of what appears in the cell left to me and in the cell above me. The cell left to where I'm standing, or left of where I'm standing in the DB table, is without the current letter in the X. So that's going to be I-1 and J. The cell at the top of where I'm standing is going to be I and J-1. Now, regardless of whether we put the I and the J on the X and the Y, I will need to always consider those two combinations, look at the optimal solutions there, and pick the maximum value, because it's going to be the true maximum or the true optimal LCS. So this is our recursive formulation. The common sequence will be 0 if the I is equal to 0 or the J is equal to 0. I already explained this before, so I'm going to reiterate it quickly. What that means is one of the two strings or both are empty. Consequently, there are no common letters. Now, if the X sub I and the Y sub J matches, I'm looking at letters that are actually matching. What I'm going to do is I'm going to grab the value of the LCS without those two letters, without the I and the J letters. So I am going to look at the cell I-1 and J-1, which simply means looking diagonally, and I'm going to increment 1 to that. So if I have previously found that I have 5 common letters without the current letter in X and the current letter in Y, I have found 5 common letters. Now they will be 6. And that's why I'm doing I-1 and J-1. Now, if the two letters I'm currently considering are not matching, I will pick the maximum of the two sequences or the two sets, where in each set there are two strings, one without the letter I'm currently considering from X, and the other one without the letter I'm currently considering from Y. And I will fill in the table as we've seen before, left to right, top to bottom. My final solution is going to be in the rightmost cell at the bottom of this table. So let's work out a more elaborate example just to show you how the DP algorithm will work. I have changed X and Y to be a little bit longer and to have more common letters. So X is A, B, C, B, D, A, B, as you see, and then Y is B, D, C, A, B, A. Let's actually try to eyeball the common letters. So there's the B appearing in the first location in Y, followed by, or matched with the B in the second location in X, and then there's the C, and then there's the A, and then there's the B. So the number of common letters is 4. Now the formulation I've already described earlier. This is our objective function, if you like, and from now on we're going to write it this way. So it is quite concise and will tell us everything about what we need to do in the table, or what the values we need to fill in the tables. We often list the initial value if one of the two inputs or the two dimensions is empty, followed by the case where we match on something, and followed by the case which we don't match on something. Okay. So if I ask you in a quiz, for example, write the objective function for the specific problem, you should write to me something that looks like those 3 lines. So this is my DP table that I'm going to fill. I've already explained that I'm going to administer or work with the letters one by one from each sequence. So you see at the top, I've kind of changed the order from last time. I have the Y, so the B, D, C, A, B, A, and in the on the x-axis, on the y-axis, I have the X, which is A, B, C, B, D, A, B. I'm listing them like this. Again, the rationale is finding the LCS count for such a long sequence or even longer sequences are difficult. If I do brute force, it's expensive. So what I'm going to do is I will generate optimal solutions to trivial versions of this sequence, or trivial combinations or small combinations of these sequences, and then I will use my optimal solution to move forward and find the solution for the more complex version or the longer sequences. So basically I will be matching A from X with B, and then with BD, and then with BDC, and then with BDCA, and then with BDCAB, and then with BDCABA. Each one of those matches is a whole problem by itself, and it's a different problem in the sense that the inputs or the sequences are different, because the X will be different than what I initially starting with. But along the way, with these optimal solutions, I am actually making progress towards finding my final optimal solution, which will exist on the bottom right corner or cell in the array. After I'm considering the A from the X, I will consider the sequence from the XAB with B in Y, and then with BD in Y, and then with BDC in Y, and it goes like this. Okay? So if you would like to find out, or if you're trying to find how many sequences are we solving, I am solving the length of X by the length of Y. So I have 6 letters in Y and 7 letters in X. So I'm basically solving 42 smaller problems, finding the optimal solution for each one of those 42 smaller problems in order to find the solution for my initial problem, which is 6 by 7 letters. So we will start by filling in the initial values, which is if one of the strings are empty, then the LCS count is going to be 0, it's empty. And that's why you see a horizontal 0 in the top row and a vertical 0 in the first column. Now, we move on to the first cell afterwards, which basically means I am considering the sequence of in X of A with the sequence in Y of B, just B. Since they don't match, what I'm going to do is I will use my third line in the objective function above. I will get the maximum of the two cells, the one on the top of me and the one to the left of me. Okay? So Ci j minus 1, I is referring to the row. So if I keep the I as is, I'm still in the same row, but if I say j minus 1, then I'm going to a different column. So it is basically the first cell in the row number 1 on the x-axis, or in the x sequence. Now Ci minus 1, which means go up one row and use the same j. So this is the cell that has the 0 just below the B and the Y in column number 1. Now I will pick the maximum of those two. From now on, I'm not going to just keep repeating myself. I will always say I will look at the left cell and the cell above me, so the cell above me and the cell to the left of me, and pick the maximum of the two. Okay? And as a convention, if they are equal, I will just pick the one at the top, which is above me. Okay, but I could have also established a convention by saying I'm going to pick the one at the left. Okay, so I'm going to pick the maximum of the two. They are equal, it's going to be the one above me, just as a convention, to be able to reconstruct the solution later on. And instead of building up a parallel 2D array of true and false values, the one I talked about before, I'm just going to put an arrow to say where is this value coming from. And I will use this arrow to later on figure out where is actually the letters that are common, or which letters are common. Okay, remember again, the table is showing me the number of LCS, but it's not showing me who are these letters. So I'm just going to use this arrow to figure that out. Okay, just to save space. Now I'm now matching the A with the D. So my first ever problem that I solved here is the sequence of, in X there is A, and in B there is, and in Y there is B. So I'm basically matching A with B. Let's call it this way, X dot A with Y dot B. Okay? They don't match, I grab the value from the top. What I'm going to do next, I'm going to match the A with D. But when I match the A with D, I'm not matching A with D, I'm matching, remember, I'm matching A from X with BD. Okay? And the answer is 0 again, because A does not match with D. Now later on, I will match A with C. Again, it's the same story, you know, it's not a match, but this 0 that I just inserted in the the result of matching or solving the problem where Y has BDC and X has A, this 0 says that there is no common sequence between those two sequences. It's not just because A doesn't match with C. In fact, it's an optimal solution to the problem where Y has BDC and X has A. And now I come to match or solve the new problem I'm solving now is X has A and Y has BDCA. So I'm going to match A with A. Now obviously there's a match. So what I'm going to do is, I've already described the logic before, I will look at the diagonal cell, and this is why I have this arrow diagonally, and I will increment 1 to whatever value appears there. The diagonal cell is basically the solution to the problem where the letter I am currently processing from X, which is the A, doesn't exist. That's why I did I minus 1. And also I did J minus 1 because I would like to omit the character I'm currently processing from Y. So that's why I look into the diagonal cell. Now, I will later on try to solve another problem, a little bit bigger. It's going to be in X there is still A, and in Y it's the sequence B, D, C, A, B. Now, A does not match with B because I'm matching one letter at a time from here and there. So I'm going to grab the value at the left. Okay, why this left cell? Because remember, I'm going to look to the cell at the left and the cell at the top, and I'll pick the maximum. Which makes sense, because really, if I have the sequence in XA and the sequence in Y, B, D, C, A, B, then the common letters is 1, which is the A. Now we will match the A with the A. Interestingly, actually this match again. But we said when we match, we're going to grab the value in the diagonal cell and add 1 to it. Someone might tell me, oh, but didn't this match before, like the A in X, or X dot A with Y dot A in the fourth location? And I'm going to tell you yes, but that's a different problem. We're now solving the problem, the smaller problem of our initial problem. This specific problem we're solving now is Y has B, D, C, A, B, A, and X has A. So since X has one A, it can only match with one of them. So I've already matched X with the A in the fourth location when that was the last letter in that earlier problem I was solving. So now if I match this, I'm going to again grab the solution without the current cell, or without the current letter in X and the current letter in Y. I will add 1 to it, and without the current letter in X and the current letter in Y, the optimal solution is 0, which is in the diagonal cell. Because without the current letter in X, there is no matches at all. And I will add 1 to it. Okay? And again, think of it common sense wise, yes, it should be 1. Okay? So we'll move on to the next row. I will repeat. B with B, yes, there is a match. Increment 1 to the diagonal value. And then B with D, there is no match. So get the value that is the maximum between the left cell and the top cell, so it's going to be 1. And then B with C, there is no match. So get the value of the maximum cell. You have 1 and you have 0 in the top, so it's going to be 1. And then B with A will not match. So we said before, if they are equal, I'm going to pick the top cell, so it's going to be 1. And then B with B, so there is a match, I will add 1 to the cell at the diagonal, so it's 2. Let's stop here and again figure out if we're doing something that makes sense. Well, I'm looking at the number of common sequences between X having A and B and Y having B, D, C, A, B. Of course, there are 2 of them, A and B, they match. That's why I have the number 2. So I should always make sure that whatever number I'm generating can make sense by just eyeballing it. Now, B and A obviously they don't match. I pick the maximum, which is going to be between 2 and 1, so it's going to be 2. And we keep filling in the rows. I don't want to drive you to boredom, so I'm just gonna move on and fill in the table in front of you, and you can ask me about this in the live sessions if you're still not sure about why these values are being generated. But I hope I was able at least to communicate the basic idea. Now we will keep doing this, and finally when we match the A with the A, where I have the sequence in the X A, B, C, B, D, A, and the other sequence B, D, C, A, B, A, then I will get my force match, which is the A with the A, and then finally the last row I will just be looking at values from the row above it, and the answer is in my last row in the rightmost cell. So I know that the count of the LCS is 4. I don't know who are these letters, obviously, but I can track through the arrows to figure them out. So to construct the actual sequence, what I'm going to do is I will look into my arrows and find out where the arrow was diagonal, because when it was diagonal, that means I have found a match and I got the previous optimal solution and I added 1 to it. So I have highlighted these guys in red here, and you can see that whenever there's a diagonal arrow, the number is actually increasing, and that will be my match whenever I added a 1. So if you'd like to start from the beginning, it's going to be B, and then a C, and then a B, and then an A. And that's exactly what we found when we looked at the strings at the beginning of this exercise. I have added these 2 slides. I would like you to review them. They will be available for you on the website, just to convince yourself that what we are doing is logically correct, and it is important in the sense that without them, without the step where we do the max, this is not going to work as expected. So I'm not going to spend time explaining these 2 slides, this one and the next one, but I've just added them for you as an exercise to work out some values and see why are we doing the maximums. Okay, so this is the same example we looked at before, except I'm showing you the impact of actually going to the left cell and the top cell to figure out which one should we consider as the optimal solution. So I am showing you first a trivial example here because there are zeros and empty string in the X, and then in the next slide I show you one in the middle, and again it will be clear to you why are we actually picking the maximum from these 2 examples. So this is just an additional tracing effort on my behalf to make sure that you got the idea. Now, in terms of coding, what we did is not a trivial example of DP. This is one of the complex examples. But when it comes to coding, it turns out to be again trivial, just like all DP code. So I have 2 for loops at the beginning that would initialize the array cells with zeros for the trivial problems where the solution is 0, and then I start doing exactly what I have been describing, but in a pseudocode fashion. So as you see here, I'm doing calculations of the objective function case by case, and then I am done. So really, the nice thing about DP again is that the coding is quite simple. It's just a bunch of for loops with some if statements, and that's basically it. So what you're looking here really is just the objective function coded, with all the manipulations we have been describing. And this is a bit higher level in coding, so I'm just using these symbolic references of top arrow and left arrow and diagonal arrow. But obviously we can again code that straightforward in any programming language. Okay. So the nice thing about this, the running time has dropped significantly from n by 2 to the m to just being m by n, because we are passing multiple times though in every string, but we pick one and we grab a letter from it, and then we go to the other one and check all the letters, and then we pick the next one, and we keep doing that until we're done. So it's really the lengths of the strings multiplied by each other. Now, to print it, here is the pseudocode for this. It is trivial. As long as I find the diagonal arrow, print the letter. Okay, that's on the axis, on the y and the x-axis, and then we are done. Okay. And the running time of this obviously is m plus n, because we're just going to go one time in all of n and one time in all of m, moving along the table from bottom right to top left. The next example we're going to look at is the Bellman-Ford algorithm for finding the shortest path in a graph. In fact, it does something very interesting. It will find us, starting from a specific vertex, all the passes, the shortest passes, to all the vertices, starting from that single vertex, to all the vertices in the graph. So it's a very interesting algorithm. It's very heavily used along with another algorithm that you will see in the tutorials, which is called the Dijkstra algorithm. Dijkstra is a little bit faster, but Bellman-Ford is more generic. It has more applications in the graph world. It is often used as a step forward in building a more complex solution, but I will not go into graph details in this course. You're already seeing enough graph stuff in this course. So here are the pros of Bellman-Ford. As I mentioned, it will find, starting from a specific vertex, all the shortest passes, or the shortest passes to all vertices in the graph. Why would this be interesting? It is actually interesting. It has many applications. If you think, for example, of taking a Uber from a specific location to a destination, the algorithm that plans your route from a specific starting point to your destination should take into account all the shortest passes to all the intersections along the way between your starting point and your destination. At least this is one way to think about it. Because if one of your roads is blocked, or if the road and what you believe is the shortest path is blocked because of a sudden accident, your algorithm has to take into consideration the next best option. And if you've calculated that up front, then and the traffic did not change in any other part in the graph of streets, then the next choice to pick is going to be readily available in the Uber software. This is at least one way to think about it. Obviously, Uber is more sophisticated than that. Uber would do something called dynamic path planning, where along the way there are a lot of changes that happens to the properties of the graph. You could have several accidents in different locations in the graph. You could have traffic congestions in different places, and there is a whole family of algorithms called dynamic path planning that is even more advanced than Bellman-Ford. But if you would like to build, I would say, a naive Uber, then your starting point would be something like Bellman-Ford. So this is the first pros of Bellman-Ford. Now, the second pro is that it works also with directed graphs. And that should give you some insight into graphs, because not all algorithms in the graph theory area will work on all kinds of graphs. So we said before that we have two broad types of graphs, directed graphs and undirected graphs. In the directed graph situation, what you have is an edge that has an arrowhead at the end that signifies the travel direction or the traversal direction. So often what works for undirected graphs will not work well with directed graphs. And in the case of Bellman-Ford, the algorithm actually works in also directed graphs. So it will work in undirected graph, and it will give you all the shortest passes from a single source, and it will do that also in directed graphs. Now, interestingly also, Bellman-Ford will work with negative weights. So I've tried to highlight here the notion of negative weights. If you look at the very simple graph I have in the middle of the screen, where it says -1 and 8, -1 is a negative weight on an edge. So again, some graph algorithms will not actually work correctly if you have a negative weight. But actually, in the case of Bellman-Ford, it will, as you will see soon, it will work correctly in the case of negative weights. Okay. It will also work with the case where you have double arrows within the same pair of vertices. Like, for example, if you look at the far left, you have an edge that will take you in one direction and whose weight is 5 to a specific vertex, and then you can go back to where you start in the first vertex to the left, following another edge that is whose weight is 8. Now, again, not all graph algorithms will work with what's called double edges like this. Now, also, interestingly, Bellman-Ford, although this is a little bit of an advanced topic, but I'm just telling you because it's kind of an interesting fact to know, that we have a problem with the appearance of negative numbers in the graph world, which is if you have a negative cycle and you're trying to compute anything and you get stuck in such a cycle, your solution will be infinitely optimal in a wrong way, because you will be stuck in a negative cycle where you keep decreasing your cost, and your cost will turn to be negative, and then you will continue on decreasing it forever, and you will never be able to stop. Like, for example, if you look at the far right, you have a simple graph that goes from from one vertex to another, following an edge whose cost is -1, and then you can go back using an edge whose cost is -2. This is called a negative cycle, and then you can go back and subtract -1, and then subtract -2, and subtract -1, subtract -2 from the cost that you have accumulated from other parts of the graph. So assuming here that this -1, -2 cycle is part of a bigger graph, and now you run into an issue. You could have reached, for example, that your cost up to now is 500, and within few runs your cost will go down to 0. But then the whole computation is just flowed, because you got stuck in a negative cycle. And negative cycles could be much bigger than just 2. It could be like a cycle that spans 50 vertices out of a graph that has 1,000 vertices. Okay, so negative cycles generally create problems in any kind of computation we do. Now, the nice thing about Bellman-Ford is that it could be specialized, it could be changed a little bit, so actually detect negative cycles. And once we detect them, we just break from them. Okay, so it's an interesting algorithm to study, actually, for many reasons. And perhaps one of the main reasons also to discuss Bellman-Ford is that this is the guy who brought us dynamic programming. This is the guy who introduced dynamic programming into computer science. So it's interesting to actually see another contribution from him, and this time it's actually a very big contribution, because again, this is a very popular algorithm. So let's start and see how the algorithm works. So I've put for you here a graph that, as you see, it's undirected, and I will start from A, and this is my starting vertex, so the algorithm will start from this. And remember, when I run Bellman-Ford, I am actually going to calculate the cost, or the optimal cost, to go from A to any vertex, not just to perhaps what you think as the last vertex, the G, the goal. No, to any vertex in the graph. Okay. Now, just like the graph algorithm we've seen in the last lecture, everything we're going to describe here will amount to a simple 1D array, which we use to track the costs that we are currently finding for reaching from A to any specific vertex. So I will maintain an entry for B, I will maintain an entry for C for every vertex, I will maintain an entry for D, I will maintain an entry for E, I will maintain an entry for F, I will maintain an entry for G, and I will keep updating those entries with the optimal, basically shortest path to go to each one of those vertices from A. So I will start the algorithm by being at the starting point, at the starting vertex, which is A. And I will track all the time how much it takes me to reach to a specific vertex. And if I ever find myself able to reach to a specific vertex in a cost that is less than what I thought I should be paying, I will update my computations. So again, I'm starting at A. And what I'm going to do is I'm going to initialize the number that represents the cost to reach to any one of those vertices with a very big number, or basically infinity if you'd like to think of it mathematically. Why? Because anything that is less than what is the current cost, then I will update it with that value. So being at A involves no cost since I'm starting at A. So the cost to go to A from A is 0. So I will, modify my entry in the A vertex to be 0. Now, I will start at this vertex A, and then I will ask who's connected to A. And I get this answer that B is connected to A through an edge whose weight is 9, and C is also connected to A through an edge whose weight is 2. So if I would like to, calculate the cost I'm going to pay to go from A to B, then I will traverse along this edge, and consequently 9 is less than infinity, so I will update B's number, or B's reaching to B's cost from A to be 9 instead of infinity. Okay? Now I will do the same for C. To go to C from A, the cost is 2. 2 is less than infinity, so I will have the cost as well. Okay, and this is what you see now in the graph. The B value is getting updated. This is the cost to reach to B. This is what I have found up till now. From A is 9. Now, the same thing is going to happen to C. I will update its cost to be 2. Now, there's no more edges connected to A, so I could either grab B or C and ask the same question again. Who is connected to B, or who is connected to C? Now, I will assume that I'm just going to take them in order alphabetically, so I will stand at B and ask the same question again. Who's connected to B? Now, A is connected to B, C is connected to B, D is connected to B, and E is connected to B. I'm going to do the same effort I've done in the first step. Now, D, to reach to D, initially, the score was, or the weight, or the cost was infinity. If I follow the edge who's dashed now, and whose weight is 3, and I'm standing at B, being at B has cost me 9, because I'm originally coming from A, because remember, these values are all the cost to start from A to reach to that. So if I say D is 12, it means I will go from A to B to D. The cost is 9 plus 3, which is 12. Okay, so 12 is less than infinity, then D will be assigned the cost 12. Now, I will also do the same thing for E. It's going to be 10, because the edge from B to E is 1, and starting from A, I have traveled to B, then to E, so the cost is going to be, to reach to E from A is going to be 10. Next, I will check the connection from B to C. Now, the edge value is 6, and I'm now standing at B. To go to B, the cost is 9, and to go to C from B, it's going to be 9 plus 6, which is 15. But actually, I have previously found a more optimal solution, which is to go to C from A, and the cost is 2. So I will not update the C value, because 15 is much, 15 is bigger than 2, so I really cannot update it. I'm looking for the optimal solution, which means the smallest value. Having done all the vertices coming out from, or connected directly to B, I will move on to the next entry, which is one level or one step away from A, which is going to be the C. Remember, we started with the A, then we moved to the B. I have the smiley face to indicate that we're now standing on the B, and next we will move to the C. Now we are at the C. So we're going to ask the question, who is connected to C? A is connected to C, B is connected to C, D is connected to C, and F is connected to C. So here's the interesting thing. When I ask, okay, what is the coast that will take me from C to B? It's going to be the edge whose label is 6. And I could be at C with coast 2 if I come directly from A to C. So 2 plus 6 is 8. It is actually cheaper, more optimal, more efficient to go to B through C instead of directly from A. So if you would like to go to B, and the optimal solution is to go to C and then you go to B, and the total cost is going to be 8 instead of 9. Since 8 is less than 9, I will update the cost to B to be 8 instead of 9. But remember, I have actually used this cost in calculating the shortest distance to E and D, since they are connected to B. So I'm going to update their numbers as well. I will calculate the difference between the two. I will subtract a 1 from 10 and a 1 from the 12 in the D. So you see here the D has become 11 and the E will become 9. Now, haven't finished yet, because the C is also connected to the A. But I'm already seeing in the A the value is 0. So if I travel back, it's going to be 2 plus 2, 4. 4 is greater than 0, so I'm not going to update my A entry, which obviously, or hopefully, it now makes sense to you. Now, who else is connected to the C? I've checked the A, I've checked the B. Now the time is to check the D and the F. Notice that if I follow through the edge that connects C to the D, the cost to go to D is going to be 4. So if I would like to find or ask who's the shortest path to D from A, it should be ACD. Obviously, the cost is much cheaper. It's going to be 4 instead of 11. So I'm going to update the D cost with 4. Now, updating the D cost with 4 should propagate to the other nodes or vertices that I have visited before are not connected to D, since I've just updated D's cost. Now B is connected to D, so I will follow the edge connecting D to B and trying to ask a question or answer the question, can I reach to B more efficiently or in a cheaper way through the D? And the answer is yes. 4 plus 3 is 7. I previously have found that I could reach to B by paying 8. So since 7 is less than 8, I will update the value for the B to be 7. And once I do that, I have to make sure that all the nodes B is connected to this change is propagated to them. And consequently, since B is connected to E, I will also update its cost to be 8. The notion of propagating the cost to the vertices that we have seen before is probably the most difficult concept to grasp in this algorithm. And here is the justification for doing that. We are processing the vertices or standing on the vertices one vertex at a time, but we don't go back. So I stood at A and computed distances to B and C, and then I stood on B and did the same, the distances to all the vertices it is connected to. And then C as well, we stood there, that's what we are actually now, and we are computing the distances, or the shortest distances to all the vertices it is connected to. Now, along the way, if we actually find a smaller number, we have to propagate actually this change to all the vertices we have seen, because we're not going to stand there again. For example, once I changed the D value from 11 to 4, this impacts the B value because it's now supposed to be 7 instead of 8. Now, I'm not going to ever stand again on the B. I mean by stand and, grabbing the vertex and asking who's connected to it and trying to do the exercise I have been describing earlier. So once we reduce the cost in one node that we have listed before, we have to make sure to go and propagate the effect of that change to all the nodes that we have seen before that is connected to this node. Okay, and that's why I updated the B and the E because of that. Now next, we are actually going to calculate the cost to go to F following the 9 edge, so obviously it's going to be 11. Okay, what we're going to do next is we're going to stand on the D and we're going to ask the same question: who's connected to D, and can we reach to those who are connected to D in a cheaper cost, or using a cheaper cost than what has already been discovered? So D is connected to C, it's connected to B, it's connected to E, and it's connected to F. Now currently I can go to D by paying 4. So if I think of going back to C, it's going to be 6. Now C is already at 2, so I'm not going to change that. Now going to B, it's going to be a 7, it's already a 7. Going to E, it's going to be a 9 instead of 10 from D. So I'm not going to update my cost. I already have found a better solution that will only cost me 8. Now going to F, it's going to be a 10 instead of 11, so I will update the F. And what do we do next? We move on to the E. We've already figured out that we can reach to E by paying 8, or the cost to reach to E from E is 8. If I go back to the B following the 1 edge, it's going to be 9 instead of 7, so I'm not going to update that. If I go to D, it's going to be 8 plus 5 is 13, is more than 4, so I'm not going to update that. Going to F, it's going to be 8 plus 3, it's 11, I'm not going to update that. Okay. Now going to G from E, it's going to be 15, which is better than infinity, so I will update that. Okay. Next we move on to the F. The F, all the other edges we're not going to update simply because the cost is going to be more. The only one that we will update is the G from F to G, because if you follow the edge there, the total cost to reach to G is going to be 14 instead of 15. And by that we are done. Okay. Now this is the exercise that we are going to do to fill in the array. Obviously, after you have filled the array, you don't know where are the vertices to follow. You will have to actually somehow track it. And again, we go back to the exercise we've described earlier, which is use an additional array to track which vertices you have to actually pass through. And obviously, the cost here is visible, because the graph is too small. It's going to be A, C, D, F, G. And the total cost is going to be 14. But we didn't just generate the shortest path from A to G, and this is really the beautiful thing about Bellman-Ford. We've generated all the shortest passes from A to any vertex. So if you'd like to go from A to E, the shortest pass is 8. If you'd like to go from A to D, the shortest pass is 4, and goes like this. And this will be our array. This is how the array will look like. These are the values that we have been accumulating. I didn't bother to show you the array before because I know this is really trivial in terms of where actually you store the values. You know already this is DP. It's going to be some kind of array, okay? And obviously there is a part that is missing from all of this discussion. How do we go about traversing the edges? This graph looks like very complex data structure. You have been exposed before to B+3s and linked lists and so on, and we will discuss later on in the course the best representation of a graph that will enable you to visit vertices and edges as in any way you like. Okay, so I'm assuming here that this will be done, but I don't tell you how it's going to be done. Ultimately, you will know how to do it, and then you will be able to fill in the array at the bottom. Now we move on to the last topic in the discussion of dynamic programming, which is that there are generally two types of doing dynamic programming. Okay, they're all called dynamic programming, or both of them are called dynamic programming, but they're actually quite different in how they proceed in terms of doing a solution. Okay, now the names, you will find them online and in textbooks, is either top-down or bottom-up. This is the more common name, but also they will be referred to as memorization versus tabulation. Okay, Now, obviously, tabulation is very clear to you. You're building a table. You're filling in some kind of an array. Now, memorization also, you use an array, but the difference between them is quite subtle. Now, all the examples I have showed you here are more on the tabulation side, because this is the harder one to get, and this usually yields more efficient solutions. Usually when you listen to online tutorials or check videos on YouTube, most of the time they're using memorization because it's much simpler to actually code. Okay, but I would like you to be able to do both of them. You will see a number of examples in the tutorial in memorization or using memorization, and you will also see obviously tabulation, which you already that's what we have been doing in the lecture. So let me show you the difference using the Fibonacci numbers that we started with the discussion of DP. Now on the left side you see the brute force code that we have analyzed before, which is 2 to the half n, or simply 2 to the n. Okay, now the code is quite simple. If n is less than 2, return 1, else do Fibonacci of n minus 1 plus Fibonacci of n minus 2, and then you go into this horrible performance where you keep computing the same Fibonacci number over and over again. The code that you have seen earlier that solves this efficiently in O of n is actually doing tabulation. If you recall the code, we used an array. We initialized the first two cells in the array with 1 and 1 for Fibonacci of 0, Fibonacci of 1, and then we started from 2, computing or adding up the previous two cells to get the Fibonacci number of the current cell we're standing at. And this will pass from the beginning of the array to the end of the array. That's why it's O of n. Okay? Now notice that the way the array is built is that we've initialized Fibonacci of 0 and then Fibonacci of 1, and then now we compute, starting because of the for loop, we compute Fibonacci of 2, and then Fibonacci of 3, and then Fibonacci of 4. So we are processing from the very simple basic problem to finally the actual, at the far end of the, to the right side of the array, we have the Fibonacci number we're looking at. Okay, this is why this is called bottom up. You go from the most primitive at the bottom and you build up until you go to your solution. Okay, your desired, your actual solution. Maybe I'm after Fibonacci of 50, but I'm not computing. I'm not starting with Fibonacci of 50. I'm starting with Fibonacci of 0, then Fibonacci of 1, then Fibonacci of 2, then Fibonacci of 3, and this keeps going until I reach Fibonacci of 50. So I go from the very simple, from the bottom, if you'd like, all the way till the complex or the big, or at the top of my computation. Okay, now this is one way to do it, and this would be tabulation. And if you actually think a little bit about this, this is what most of the examples I have showed you are doing. Okay, we go from the very basic simple version of the problem, and then we keep making it harder and harder and harder by considering the more complex version of the problem. So if you think of LCS, for example, this is what we did. If I get two strings, each of length 100, I don't look at the 100. I start with a string of length 1, another one of length 1. And then I will fix one of them to be of length 1, and then I will go on increasing the length of the other one. So I'm going from the very basic, from the bottom, all the way to the final solution. Okay? So LCS is also, has been shown to you using tabulation. Now, let's see how memorization is done. Recall the problem with the Fibonacci code that I have showed you earlier, the brute force code, is that it keeps recomputing Fibonacci terms that has been encountered before. For example, Fibonacci of 2 is computed here 3 times. If you look at Fibonacci of 1, it's computed 1, 2, 3, 4, 5 times. Now, memorization thinking goes like this. We will code the recursive code just like what we have seen in the brute force version, but we will add additional statements to check before we try to compute any term we face if we have seen it before. And what that means is every time we compute a term, we will have to store it somewhere so that the next time, if we happen to see it, we are going to retrieve it from our storage instead of recomputing it. So instead of doing the 2 to the n that is in front of us here, the performance will enhance drastically because we are saving lots of computations. This is the idea I was just telling you about. So I'm just going to show you for the implementation of this idea just for Fibonacci of 2. So what we do in the memorization version is we will keep an array of results. It's basically a key value pair where the key is what is the computation that was involved and the value is the result of the computation. So I have listed here the Fibonacci terms that we will encounter for this specific example, and we will start this code because it somewhat resembles brute force, although it is not brute force. We will start from the top. That's why it's called top-down approach in the DP literature. We will start with Fibonacci of 5, but we haven't actually computed yet any Fibonacci for that matter, which will take us to trying to compute Fibonacci of 4 plus Fibonacci of 3. We haven't computed anything yet for Fibonacci of 4 and Fibonacci of 3. Let's say we process Fibonacci of 4 first because we're going to do n minus 1 plus n minus 2. So we will try to solve Fibonacci of 4 first, and that will take us to Fibonacci of 3 and Fibonacci of 2. Again, we're going to move from left to right, so we're going to process Fibonacci of 3 first, which will take us to Fibonacci of 2. Okay? Now, whether you process it from left to right or right to left, the point is the first time you reach to any numeric result, and you do that when you hit the base case in the recursion, so you will get Fibonacci of 1 plus Fibonacci of 0, you add them up to get the Fibonacci of 2. The first time you ever compute Fibonacci of 2, you will store it in the table, which is shown by the red arrow from the recursion tree to the array at the bottom. Now, any later instance where we start to ask again, what is Fibonacci of 2? The first thing we do is we go and look in the table, have we computed this before or not? And indeed we would have computed this before, so what we're going to do is we are going to retrieve it 2 times from the table for the 2 more times where we ask what is Fibonacci of 2. So we're not going to go into the recursion that takes us to Fibonacci of 1 and Fibonacci of 0, which is shown over here. Okay? So obviously this is a big improvement in performance. This is the general idea how we do memorization. We are storing results, but notice this is not brute force modified. This is actually dynamic programming. But it's a different way of thinking about dynamic programming because I always start by coding as if I'm coding recursively, but I prevent myself or prevent the code from going into unnecessary recursive codes by storing the results of intermediate computations. And that means every time I do a computation I have to store it, and every time before I do a computation I have to check if I have done it before. And this would be the code that I am describing to you. Now if you read this, you will notice that it's somewhat similar to brute force, but this is not brute force, this is DP. Okay, except it's a different way of doing DP than what you have seen in the previous 5 examples in this lecture and the previous one. Okay, if you read the code from the top, it says if n is equal to 0, return m of 0. If n is equal to 1, return m of 1. This is pretty much doing the same thing as the if statement on the left in the brute force version. Now if Fibonacci of n minus 2 is not calculated, regardless of what n is, so if I start with n being 5, then I'm talking here about Fibonacci of 3, and the next statement, the next if statement is going to be Fibonacci of 4. Okay, so here I switched the order, okay, compared to what I discussed in the previous slide. And it doesn't really matter whether you do Fibonacci of 4 first and then Fibonacci of 3, or you do Fibonacci of 3 first and then Fibonacci of 4. And either way you have to do this 2-way recursion. Now, if I have not calculated it, it means here go and look in the array of results to see if actually you have a value for this computation. Now, if it's not calculated, then you call the Fibonacci and move on to the next deeper layer in recursion, and ultimately along the way you will store the results, and then when you come back from regression, you're going to do the addition, which is the what you're looking for. The Fibonacci of a specific number, n minus 1, n minus 2. Okay? Now, I hope I have given you a kind of crash course in memorization. I don't particularly like it, although I will not prevent you in a quiz or a midterm or an exam to use it. The problem with memorization, it will give you a dynamic programming algorithm. It will perform definitely better than a brute force approach, but it will never be as efficient as a bottom-up approach. Okay, bottom-up approaches are generally a little bit faster. They just involve a simple array, whether a 1D or 2D, and you fill the array using a for loop. So and maybe a bunch of if statements inside it, but there is nothing more than this. While here we start to see recursion, and this obviously will take more stack space. It will be a little bit slower as well. So to summarize, there are two techniques. Memorization, you assume that you already have computed all the subproblems and that you have no idea what the optimal evaluation order is. This is an important observation. You know, what I'm doing in memorization is I'm just using a storage space to record everything I'm doing. Okay? Now, after I'm done, I have to figure out somehow what is the optimal solution. So I could typically scan through my results to figure out what is the optimal solution. So unlike, you know, the tabulation where you know the optimal solution is going to be at the far right bottom of the table, here this is not necessarily the case. What you're doing here is basically you're just storing temporary computations or solutions that you are generating, but the notion of you're actually has solved the problem, or where is the solution is coming from, or which one is the best approach, you know, the optimality issue. It's not really clear when you do memorization. Okay, sometimes if the problem yields itself to have that clear, that's one issue, but the general case is what you're basically doing here, you're just using an additional storage to store the results. Okay, and then you figure out what have you been doing later on. Okay, what is the optimal solution, and how can you actually retrieve the equivalent result. For example, in a graph where you calculate, you would like to know the vertices that will be the shortest path. Okay, so this is something to worry about with memorization. It's not impossible to be retrieved or to find this information. It's just a little bit harder compared to tabulation. And this is what I try to emphasize in this slide. Let me read. It says typically you would perform a recursive call from the root and either hope you will get close to the optimal evaluation order or obtain a proof that will help you arrive at the optimal evaluation order. Okay, so usually there's always an additional effort after you're done to figure out what is the optimal solution and how can you actually make sure that this is the optimal solution. Okay. Now, on the other hand, tabulation, as you know now, is the filling in of the array from the trivial case, the smaller version of the problem, all the way till the bigger version of the problem that you're really targeting. And I always find students shy away from tabulation because it requires an in-depth thinking about the nature of the problem. How can you actually devise a substructure that you could use to solve the problem bottom up. The ideal example that would come to my mind here is LCS, the longest common sequence. You really need to think hard to understand what you should do when the two letters you are actually comparing are not matching. It is not trivial. You need some training to be able to obtain such substructures and such objective functions. Okay. And obviously all of this doesn't show up in the memorization version because you're just going to do some recursive coding. However, as I mentioned, tabulation will always, in most cases, will be much faster compared to memorization, even though they are of the same asymptotic order, but the constant beside the n will be quite different in tabulation compared to memorization. Okay. So I feel that students shying away from tabulation is a result of the lack of training from the student part in actually building solutions that are bottom up. but in most cases, if you really care about performance, you need to be able to do tabulation. I will finish my discussion of tabulation with one last note, which is that all the examples you have seen up to now, except for the first one, which is quite trivial, when we talk about tabulation, we think of a table or an array, a 1D array or a 2D array. But this is not always the case. Sometimes what you construct and apply DP on bottom up will be an array that has certain holes in it because of the nature of the problem. So it will not look at the end after you filled it in as a table of values as much as maybe it's a tree or any kind of staircase kind of design. So it's a tree kind of tilted to one side. So you don't actually have to always have solutions to every cell in your table. Sometimes the solutions are not defined. Okay, but you can still do it bottom up. Okay, I will show you one example we have seen earlier because really it had this, but there are more sophisticated examples you will see in the tutorials regarding this issue. So here is the example I was referring to. If you look actually at this very trivial example we looked at in the first lecture about DP, where we summed the multiplication of values within a certain range, there was an area in this table that wasn't defined that I've kind of put here in pale yellow. Really, the values based on the problem statement starts to appear from the number 2, which is the multiplication of 1 by 2, okay? Because the second term on the n has to be greater than the m. So our first term that this problem is applicable to is 1 by 2. And it will go by, all the rest are applicable within the area that have values, okay? So 1 by 3 is valid, 1 by 4 is valid, 1 by 5 is valid, and so on. 3 by 4 is valid, 3 by 5 is valid, but 3 by 3 is not valid, so there's no solution there. So what you end up with here, this obviously doesn't look like, if you remove the space that is highlighted in yellow, this doesn't look like a 2D table anymore, okay? If you remember from CS2 days, we talked about ragged arrays. This looks like more or less a ragged array, or perhaps some other structure. It doesn't have to be, to look exactly like this, okay? So don't always stick to the idea that you must have a solution. Sometimes there is no solution based on the problem statement. I will conclude today's lecture by referring you to the textbook and the pages within each of Corman and Goodrich textbooks that you need to read. And as I mentioned before, start with Goodrich, it's a light read, and then move on to Corman, and you get the really dense stuff and a lot of in-depth remarks by the authors about the topics discussed.